Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Manna. Say hi.
Hi, my name is Manna. I'm currently a third year math and statistics year at Exeter College in Oxford.
Brilliant. And Manna's going to tell us about some maths in a minute. I also want to shout out to Jade, who is moderating chat today. It's Jade's first time moderating chat. Say hi to Jade in chat, and hello to you as well, watching at home. People around the world, wherever you are. Hey, we've got a math stream. I've got two announcements on screen, two things that I'm supposed to show you. One of them is Promise Europe, which I remembered to mention last week, and I'm mentioning it again. That's a summer school in Oxford. And one of them is an essay competition with St Edmund Hall, which is one of the colleges in Oxford. And that's an essay competition where there's a small prize for the best entry, but more importantly, there are loads of other people's essays that you can see out on that link. If you go there, even if you have no intention of writing a maths essay for this competition, you can see now quite a few previous entries and things. There's a £50 prize for the best overall and a separate £50 prize for the best student. There's an age limit on that and some rules about who's a student. Let's see, I think that chat message is people saying hi Jade. So there we go. That's maybe proof that the audio is working, which is nice. I'm kind of interested. Is it also proof that Jade's here? We'll find out. Yeah, good. Okay, right. I think we should do the poll that we usually do while we're getting people in the room and people are working out how the chat's running. Oh yeah, link to chat is at the bottom of the screen, and also taking place in the YouTube link below. Gosh, what are words? What are words? We always do this poll at the start. Manna, I didn't tell you about this. The poll is got a 5-star options for how was your day today. I guess start with us. How was your day today?
No, it was really good. I have nothing to do today prior to this, so it was good.
Okay. This is your first thing today. Pretty good. So you're third year now. So your lecture timetable is a little bit complicated, right?
Yeah, I don't have anything today.
Okay. I remember in the first year we try and make sure that it's nice and evenly spread out, but then
Yeah,
third year, okay. And maths and stats, does that mean some of your lectures are over in the statistics department? Or not so
yeah,
much.
most of my classes are in statistics, and also I'm doing a project, so that means I'm taking even fewer classes.
Right, okay. So that's pretty good. What's the project on?
Orthogonal polynomials, which is not related to stats, nor the thing we're going to talk about today,
Yeah,
but it's interesting.
okay. Nice. I think I'm having a 4-star day. I don't know. I had a meeting this morning where I had to tell people about live streams, so that was nice because I like telling people about live streams. And then I had a meeting this afternoon where we just talked about admissions, and that was much less fun. Let me have a quick look at chats. People are voting for 3 and 4 and 5 stars. I'm always watching out for people who vote for 1 or 2 stars. It looks like that today. That is nobody, which would be really nice. Let's leave that running. Chat's running behind the scenes. Miles is doing promise problems as charts upon a partial solution. I think if you mention it in your write-up, be honest. But I think be honest. Say I saw the solution and it looks like this. Maybe discuss it. Maybe extend it a tiny bit if you can, or do something slightly different. The promise thing is marked by humans who are very excited. I don't know how the essay is judged. I think there's a panel for judging the essays. Kite wants to know how essays work. People are saying hi to Jade. People are saying hi to Manna. Jade has said hi to prove that Jade has also found chat. Hooray! Great stuff. Somebody's voted 1 star just as we were talking. Really sorry if that's you having a 1-star day. I always say that, hey, if you're having a 1-star day, at least you've come to find some maths. How many spots are in the Promise Summer School? I think it's about, off the top of my head, I think it's about 20. It's not a huge thing. It's a kind of small group of intense mathematics people. It's really fun though. It's downstairs in the maths building. I'm pointing downstairs as if, off screen. That's just like the whole downstairs world. Sorry, I'm talking too much. I should hand over to Manna because today's topic is surreal numbers, right? Which is something
Yep,
I don't know anything about. I'm looking forward to learning about surreal numbers. Over to you, Manna.
he's scrolling up. Yeah, so the topic I'm going to share with you today is surreal numbers, which is a really niche area in math. By that, I mean it's not something that you would do at university, at least not that I'm aware of. If I were to describe it, I would say it is really elementary math with a lot of imagination. I really like it, and I hope you'll like it as well. So before we get started, I would like to ask you this question. What is a number? Oops. If you have any ideas, just put that in the chat.
We're starting with the big question. We had Sakai, math and philosophy person, on last time. What is a number, chat? It's a bit like chat asking me what maths is a couple of weeks ago as well. Maybe they'll be happy. This is more concrete, right? What's a number?
Yeah.
You know one when you see one, I guess. I just got that. There we go. Let's get that a little bit more like that. Good stuff. People are telling us about numbers in chat. Here it is. Somebody said, oh, can you see chat as well?
Yeah. A number is what I write in my calculator. That is very good response.
I can write a lot of stuff on my calculator. But they've got a point, right? My calculator's got some numbers on it, right?
Yeah.
I can see them.
Yeah.
It's these ones, right? An abstraction of amounts of stuff. It's got a thumbs up from an anonymous person. I like that one as well. Two people are talking about cardinality, which is not something we've talked about in the maths club before. Does that mean something to you, Manna?
A cardinality of set is natural numbers, so it's like this. The size of a set is natural numbers. You can have a size of 0, you can have a size of 1. So that is correct in a sense, but we also, that's like natural numbers, but we also have a lot of other numbers. So matrices and vectors, wait, that's going too fast, I can't read.
So someone's pulled out matrices and vectors as they work a little bit like numbers. I think we'll start some sort of argument in chat about whether they
Right.
whether they.
So some of the comments are really abstract, and some of the comments are about like a specific type of number. So we have we started with positive integers, and then we extended that to include 0, to include the negative numbers. We also include rational numbers, real numbers, and even complex numbers. So the idea of number is really not trivial. But today we're going to give a very specific definition that you can explicitly write out about surreal numbers. But just a warning that the definition is actually quite complicated. So take your time to read through it. If you have any questions, just put that in the chat and we'll go through your definitions in a bit.
And surreal means weird, right? Is it kind of a joke? Because it sounds like real numbers, but surreal for weirdness. Anyway, they're weird.
They're invented by a really interesting person, John Conway. He's my favorite.
Can I zoom in on this a little bit? Okay, so I'll read them out, I suppose. You've got 2 rules on the screen for making surreal numbers. I guess every surreal number is a pair of sets using previously defined surreal numbers. So that's already a bit circular. You've got a left set and a right set, and you're writing those. So your surreal number x is written left bracket, and then xl is that left set, and then xr is the right set. Okay, so 2 sets with a bar in between them and angle brackets around the outside. That's how you define a new surreal number. And there's a rule that no number in x left is greater than or the same as any number in x right. Oh my goodness, okay, so what am I imagining? I've got some stuff on the left and stuff on the right, and the things on the left are supposed to be less than the stuff on the right. But everything is a surreal number, right?
Yep.
Okay. Yeah, matrices and vectors maybe do follow some of the same axioms as our number systems. The piano axioms are the famous ones for counting numbers. I'm not actually sure how many of them, off the top of my head, I think vectors do. Anyway, sorry, surreal numbers. You've got rule 2 as your definition of what it means for y to be bigger than or equal to x. Basically, surreal numbers. No number in x left is greater than or like y, and x is not greater than or like any number in y are. I think we need some. Yeah.
Right. So X and Y here are numbers that we're thinking about. They're surreal numbers that we're thinking about. And XL, XR, YL, YR are sets. So they are the sets that we have mentioned here. And the sets would contain previously defined numbers, which is something to think about. And then we have this additional requirement that no number in XL is greater than or like any number in XR. And when we have these two numbers, X and Y, we can say Y is greater than or like X. If no number in XL is greater than or like Y, and X is not greater than or like any number in YR.
Gosh. So you're comparing that set, and there's some confusion. We're comparing any number in that set compared to the number, but then that's sort of recursive, right? Because that comparison is also about surreal numbers.
So there are a few questions in the chat. I'm just going to answer them first. So every surreal number is a pair of sets of numbers. Yes. So by a pair of set, it is the XL and XR, a pair of set, YL and YR, another pair of set. And how can we compare XL to Y?
You're comparing each number in.
Not comparing XL to Y. We're comparing the elements in XL to Y. So the elements in XL are numbers. XL itself is a set, and Y is a number. It is a pair of sets, but it is a number. So we're comparing the numbers in XL and the number Y, if that makes sense.
I mean, it's highly recursive, isn't it? Like, rule 1 is recursive because you've told me that. I think every time you say number, you mean surreal number. So rule 1's recursive because you've said to make a surreal number, please get 2 sets of surreal numbers and write them down in this picture. And that's recursive because how am I going to do that until I know some surreal numbers? And then your second rule is also recursive because it says we can compare the surreal numbers, but the comparison works by comparing the number to one of the sets of to the elements of one of the sets of surreal numbers, which in itself is then, in order to do those comparisons, it's more surreal number comparisons. And to link them together, the way that surreal numbers are defined involves this comparison between things on the left and things on the right. So there's sort of this knotty, combined, kind of complicated setup of things that should be less than other things, but recursively defined. Like, how do you know anything's less than anything else, I suppose? So this XL and XR, there's a question to... So you're writing underscore, I think, to mean with a little letter.
Yeah.
So that's pronounced XL, and it would normally be written like at the bottom of the screen, X with a little subscript L.
They're like a big X and a small L.
Even though that's a lowercase x and a capital L. Yeah. The underscore thing is good for if you have to type text. Maybe you're trying to send someone an email about surreal numbers, and you don't know how to do subscripts in emails. Hey, or maybe you're trying to explain your chemistry homework over Discord or something, and you want to just type up. You can have that for free. Underscore for subscript. What's the symbol for superscript?
This thing?
Oh yeah, the caret thing above the number 6 key. We're learning about typesetting today. We're learning about mathematician code for the concepts of subscript and superscript. That was good because you can write powers. Like, some things like Desmos, I think, even interpret that as powers, which is quite nice. Welcome to the Maths Club, by the way. They said it was their first session. Hi, welcome to the Maths Club. Please keep asking questions. Ooh, look.
I wonder if it work if we typed this thing. Yeah, it would. So this bracket will say that the entire thing in the bracket will go into the subscript, whereas we only have one thing, so we don't need that bracket.
We're getting too much in typesetting. Hi, Arjun. We've just started. We've just started. We're talking about surreal numbers. We've got a definition of surreal numbers on the board, but it's highly confusing because it's really interconnected and really recursive. So we're trying to understand this definition of something called surreal numbers. Welcome to the live stream. Okay, so you want me to take sets of surreal numbers and glue them together to make new surreal numbers, but being careful to do lots of comparisons along the way. The comparisons are also defined recursively on subsets, on comparing elements against elements of sets. Recursively. Yep, okay.
I guess the first question is, does this definition even make sense? Are there anything that satisfy the definition of a surreal number? Oops. I'm going to scroll up a little bit.
Yep, that's right. That works.
Right. So can you come up with any number that satisfy the definition?
It's going to be a very short live stream if we can't, because if there's no surreal numbers, then job done.
So there's a question in the chat, how is Y both a number but also a set of numbers? So a surreal number is defined to be a set of numbers, so by definition it is a number but also a set of numbers, which is quite tricky.
Yeah, maybe people would be happier if we didn't say the word number. If we said this is the definition of some hippos. A hippo is made by, you take two collections of hippos and you merge them together. That's what a hippo is. Maybe somehow the kind of any intuition we've got about numbers is maybe unhelpful.
Is this anything to do with games? Yes, we'll play some games at the end, which is highly related to surreal numbers. However, if there is no predefined numbers, yes, that is the question, and that is like the thing to think about when we're defining our first number, which is tricky.
So yeah, if I'm building my surreal numbers out of other surreal numbers, how do if I haven't got any, then I probably can't think of any more. Lots of recursive things need a sort of starting point, right? Like if you're doing proof by induction, you need a kind of basis case. You need something to start things off. If you've got recursive functions, you're often told the first number. Yeah, I think chat might be trying to prove that there aren't any by proving that it would have to be smaller than the previous. Yeah, okay, right. Do you want to help us out then? I think there is one like special defined surreal number.
Right. So I'm going to review the answer.
Oh, okay.
So oops. Just
is that 5
this
for the
is the type of empty set. So by an empty set, it means that there's nothing in a set. It is empty.
Okay, so you want to say that is your first example of a surreal number. Take the empty set, another copy of the empty set, the set with nothing in it, and glue them together, open bracket, empty set, vertical line, empty set, close bracket.
Right. There was a comment just a second ago, I didn't read it. Can you start with the empty set? Yes, that is the right answer.
Yeah, Liam's great. The right side of a hippo, we've got to check that that's bigger than the left side of the hippo. In order to do the hippo comparison, you need to know the definition. Let's first check the hippo against the contents of the left side of the other hippo, and then check the second hippo, check its right side against the entire other hippo.
Right, and we can also check this against the first row. So it is a pair of sets. These are both sets itself, and it is made up of previously defined numbers because it is made up of nothing. And then no number in a left set is greater than or like any number in a right set, which is also trivially true. So that is by definition a surreal number.
That's amazing. So I said something wrong. I said that this was like a special definition of a surreal number, but it's not, is it? It just works.
Yeah, it just actually satisfied the definition.
A minute ago, we had no surreal numbers, but even armed with no surreal numbers, you can still construct the empty set. The empty set's got nothing in it. If you don't know any surreal numbers, you can still build the empty set.
So there was a question, is the empty set less than the empty set? We're actually not looking at the empty set, we're looking at the elements in the empty set. So remember we have that no number in XL is greater than or like any number in XR. So we're not looking at XL and XR, we're looking at the stuff in XL and the stuff in XR. And since there are no stuff at all, it just holds trivially.
Loads of stuff is true about the empty set. Like, all the numbers in the empty set are bigger than 6, I think.
I thought serial numbers are pairs of sets of numbers. Indeed.
Pairs of sets of surreal numbers, right?
Yeah,
I think every time we say numbers, we're going to mean surreal numbers for today.
Yeah. We're going to secretly think about these surreal numbers as numbers, but they're still... So we're going to relate surreal numbers with the actual numbers.
Oh gosh.
But they're expressed, like everything here will be surreal numbers.
I'm still marveling about the way you've built something out of nothing, by the way. We knew no surreal numbers, and then used that information to say, well, I'll write down the empty set. The empty set is a set of surreal numbers. It's a set of numbers as well, it's a set of hippos, or whatever. So then we can write that down as XL, write that down as XR, and hey, now I've got a new surreal number. Where it's still true that no surreal number in XL is greater than or like any number in XR, because there are no numbers in XL or XR. I don't have to worry about comparing anything because there's nothing there.
Okay.
This is ridiculous. We've now got a surreal number.
Yeah, so now we have accepted that this is a surreal number. I'm going to secretly call this 0.
Ooh.
As in the 0 in the real world. Now, when I call this 0, I'm implicitly assuming something would be true. For example, 0 plus something would be that something, 0 times something would be 0. And it turns out that it is actually true. There are definitions about adding and multiplying surreal numbers, but that's not what we're going to cover in this episode. So we're just going to assume that this does exactly the same thing as 0.
There's a couple of suggestions in chat. I'll summarise them. I think people want to consider instead building surreal numbers out of real numbers, to have those sets be sets of real numbers that you then stick together. Somebody wants to use 0, and somebody else wants to use 0, 1, 2, 3, 4, 5 on the two sides. I guess the interesting thing that's going to happen is that we can build surreal numbers out of nothing. We don't need to start with the normal counting numbers and use them to build stuff. We're going to build them out of like the empty set and build substance out of nothing.
So the issue with open bracket 0 vertical bar empty set is that we don't have a definition for 0 yet. So 0 has not been defined in our surreal number world. So that is something that would be valid, but we don't have it yet, if that makes sense.
Yeah, somebody else in chat has just said, what is 0, 1, 2 if we haven't defined it yet? So we're doing some sort of definition stuff to start from really tiny axioms. Oh gosh, I'm actually quite scared of this making something out of nothing. Although the thing we've made is called 0, so I guess we've made nothing into something.
So would this empty set, vertical bar, empty set, vertical, empty set be another example? Yes, exactly. This is how we're going to build our second number. So for simplicity, we're just going to write this entire thing as 0. And the person in the chat was asking if this is another number. So to check if this is another surreal number, we're just going to check the definition. Is it a pair of sets? Yes. So this is a set and this is a set. Has it been previously defined? 0 has been defined, and everything in the empty set has been defined. And then we also need that no number in XL is greater than or like any number in XR, which is also vacuously true because there is just no number in XR, the empty set. So we can put 0 on the left and empty set on the right, and this is still valid.
See, now that you've got like one foot in the door, you've got a surreal number, and now you're going to start putting it in sets and making things.
And related to this idea of defining a number in this way, by symmetry, there is another number that we can define, which is empty set 0. We can also check that this satisfies the definition of surreal numbers because it is a pair of sets. The sets contain previously defined numbers, and no number in the left set is greater than or like a number in the right set, because there's just no number in the left set at all.
Yeah, relying again on the fact that the empty set's got nothing in it, so it's quite permissive, loads of stuff. Oh
no. Right, so after we have secretly called this thing 0, we want to give a name for the two things that we have constructed out of them.
What do we think, chat? We're gonna give names to these two new surreal numbers. They're totally different because there's actually quite a big difference between the set that contains 0 versus the empty set. The emptiness is different. Emptiness
yeah, that is the symbol for empty set. My handwriting is really bad. Sorry, what was going on just now?
I dropped the internet, I think.
Okay.
We're coming back? Yeah, we're back. I think we're possibly back live. I don't know if anybody's still watching. I don't know how chat's doing. Yeah, stream broke for everyone. I think the last thing I said was, I think I dropped some frames, and then everything went off. I'm going to wait until chat tells us that we're back. Sorry, chat. Have I lost you again? Oh, right, okay. We're going to wait until chat says we're back. I'm just going to say some random stuff until then. Yeah, gosh, these are real numbers. So you're building something out of nothing, and then as soon as you've got a something, you start using that to build more stuff as well. Everything says connection restored. We will see. People in chat say it's back, so we're going to keep talking about surreal numbers.
Okay.
Sorry, Manna. Carry on.
Okay, I was so panicked for a minute. Okay, so people have mentioned the idea of naming them 1 and -1. So the question is, which one should be 1 and which one should be -1?
Is one of them bigger than the other?
Yeah, so we have the definition of greater than or like, and secretly we want the thing that is called 1 to be greater than or like the thing that is called -1. And we want 1 to be greater than or like 0, and 0 to be greater than or like -1.
Okay. And I can see that comparison is going to involve... It might involve comparing 0 against 0.
Right. So, can we show that if we're going to call this 1 and if we're going to call this -1, will there be any contradictions? Will there be anything that doesn't hold anymore?
I guess there's lots of comparisons we could be doing now, right? We could be comparing 1 and 0, 0 and -1, or the things that you're calling 1 and 0 and -1. I kind of want, like, choose 2 different comparisons that I might want to try out before I'm happy calling them 1 and -1 and 0, I suppose. Yeah, I want all of these. These feel quite hard to check.
Okay, so if we want to check this thing, so we just go by the rule 2. So no number in XL, so this is supposed to be Y and this is supposed to be X. So no number in XL is greater than or like Y, which is trivial. And X is no greater than or like any number in YR.
Which is the empty set there.
Mm-hmm.
See, so because the comparison definition in rule 2 only looks at XL and YR, if those things are both the empty set, then we've still got this kind of trivial comparison.
Right, yeah.
Okay.
And then would the other way around hold as well? So can we show that this thing hold as well.
Do we want it the other way around, or do we want?
So I guess the thing we're showing is that which one. So we have shown that y is greater than x because no number in XL is greater than or like y, and x is not greater than or like any number in YR. And whoa, okay, I'm a bit confused myself.
Yeah. I think the first thing you wrote there is true, that the empty is bigger than empty 0. But then the next line down, I think that empty is going to turn out to be less than or equal to 0 empty, I think.
Yeah, and we can't show this direction because we want to use XL, and XL would be greater than or like 0 because, well, we can show that 0 is greater than or like 0, if that makes sense.
Yeah,
okay, so
we can't prove that one, and actually I suspect that...
We can prove that.
Oh.
We can, so 0 is greater than or like 0. So this is 0 greater than or like 0. So what we can show is that y is greater than or like x. If no number in XL is greater than or like y, this is true because XL is the empty set, and x is not greater than or like any number in YR because YR is also the empty set. So we can show that 0 is greater than or like 0.
Okay. So this is the set comparison idea. It's really subtle. I think this one here, I can't really, I can zoom in on it, there we go. This one here, so this is a good example of this thing on the left being bigger than the thing on the right. The way the comparison works is you compare, oh gosh, can you help me out? You compare XL, which is the empty set, versus the number on this side, which is this entire object over here.
Yeah.
So the elements of XL. I'm always going to get that wrong. The elements of XL against the whole thing over here, and we don't actually engage at all with what this thing is or means because there are no elements in that empty set.
Yeah. So it's just trivially true.
And then the other way around is the other thing we're supposed to check is we're supposed to check all the elements of this are bigger than this surreal number on the right hand side. There we go. Bigger than that entire surreal number on the right hand side. And again, we don't really have to engage with what the surreal number on the right hand side is or means because this is the empty set here, so all the elements of it, there are no elements of it. So it's easy to say that all of the elements of it are green and have little spots. All the elements of it are bigger than the surreal number on the right hand side because there are no elements. I'm a bit suspicious about my internet connection again. It's going to be fine. There might be some buffering. We might have turbulence ahead. Yeah, if there, Kai has got a really good point, which we'll just push into chat here. If there were numbers, how would you compare them? Manna, do you want to take that? So we've been getting away with loads of empty set stuff. If there were some numbers around, how would we compare them?
So there are actually like two ways of thinking about it. When we're saying that every number in something satisfies some criteria, it could be that there exists some number in that thing that satisfies the criteria, or it could be that no number in that thing, there isn't any number in that thing that doesn't satisfy the criteria. It's a bit confusing. So like, it's whether we require the existence of a thing that satisfies the criteria in the first place. So in this context, if we don't have anything at all, we will say that the empty set, every number in the empty set is 17, for example, and that is true in our case, because there is no number in the empty set, so there's no number that doesn't satisfy the criteria of equaling 17. It's not a natural way to think about it, but it's convenient for us here.
the empty set is extremely weird. You might think it was nice and simple because it's got no stuff in it, but loads of things are true about the empty set. Every number in the empty set is prime. Every number in the empty set is composite. Every number in the empty set is 2. It's just...
Yeah. So we're not requiring a thing that satisfies the property to exist. We're just saying that no number, there isn't any number that doesn't satisfy this property.
This is a general thing that if your statement has no counterexamples, if your statement has no counterexamples, then it's true.
Right.
Sometimes there might be no counterexamples for a really obvious reason, but that still counts. So we're making lots of statements about the elements within that set, and because there are none, loads of stuff's true about those. If there were some elements around, if we were trying to do a comparison on 2 of these sets, pairs of sets, and there were numbers in there, we would have to compare those numbers, and it's recursive, I suppose, in a way, that we want to go dig down and compare those numbers. In the surreal numbers world, those numbers themselves are pairs of sets, and we would compare them in the same way and keep drilling down.
So up here we have already compared 0 and 0. We have shown that 0 is greater than... Okay, somehow I can't scroll this.
Oh, sorry. Got you. Okay.
Right, so up here we have already shown that 0 is greater than or like 0. And we can show here that 1 is greater than or like 0, and 0 is greater than or like -1. And one thing that is true about the real world is that if x is greater than or like y, and y is greater than z, then we have x is greater than z. So this is called transitivity, and it kind of frees us from having to compare x and z again. It is a really nice property. And it turns out that this is also true in surreal numbers. There is a legit proof, but we're not going to do it here. We just assume that we have 1 is greater than or like 0, 0 is greater than or like -1. Then we also have 1 is greater than or like -1.
Good. Okay. Yeah. So you've kind of established some numbers, or things that behave a tiny bit like numbers now. You've got... I can kind of see that symmetry thing feels a bit like negative signs, maybe. Can we keep going?
Right. So once we have 1 and -1, we can build even more numbers from what we have. So based on the same idea as putting 0 in the left, empty set in the right, we can have stuff like 1, 0. They might not satisfy the definition, but it is a possible surreal number. So by might not satisfy definition, I mean that it might not satisfy this part of the definition that says no number in XL is greater than or like any number in XR. We know that this is not valid because 1 is greater than or like 0. So this is not a valid surreal number. But we might be able to do it the other way around. And we can actually show that this is actually valid.
But have I got a choice? I've got other ones I can build, right? Okay.
Yep.
So maybe I'll take your word for it that defines a new surreal number where we'd have to do some comparisons to say, that set on the left is the set containing the surreal number 0-ish, and the set on the right is the set containing the surreal number 1-ish. To compare those, I'd have to look at all the elements inside those sets. No, the lefts and the right parts of those sets. I'm getting dizzy. And well, that's fine because we decided that.
So this is not valid because 1 is greater than or like 0, so it doesn't satisfy this definition here. And then this is actually valid. You can also verify that. Because 1, no number in the left set is greater than or like any number in the right set. 0 is not greater than or like 1. So this is a valid number. And we can also call it some number. And just a spoiler alert that I'm going to call it 1/2. And I'm claiming that it does 1/2 does. So if we're thinking about 1/2, we know that 1/2 plus 1/2 is 1. So with the definition of surreal numbers, with the definition of addition of surreal numbers, we can actually show that this thing plus itself is actually 1. But we're not going to do it here. We're just assuming everything is true. And if you want to know how addition works, you can Google online. There are many other resources as well. So what is the formal name for these?
Surreal numbers, right? They're just called surreal numbers.
Yeah. So these are surreal numbers, and they're explicitly written in these ways, and we're just calling them the numbers. We're assigning them a number in the real world, and we say that it does what exactly the other number in the real world does.
Okay, so the surreal numbers we've found so far kind of behave a little bit like the actual numbers 0, 1, minus 1.5. Okay. Can we build any more? Can we keep going?
Yeah, so in the next step, we would have like 1, minus 1, 0, and we have all of these things, new things that are like 1/2. We also have minus 1/2. As an exercise, you can try to figure out what represents minus 1/2. There are also 2 and minus 2. So these are the new numbers that we have to find, and we can put them in the left set, in the right set, and see if that actually means something that is valid.
I'm trying to guess what I think minus 1/2 would be, because earlier I thought that negation was like flipping them, but that's not allowed for this 1/2.
Well, we could do minus 1, 0.
We've got minus 1. We've got
right,
minus 1.
Yeah, we got minus 1 and 1.
I forgot we have minus 1.
Yeah.
Okay. Huh. Can we do empty set line? Can we put empty set on the left and 1 on the right? Is that allowed?
Yes, and we can show that it is 2.
Oh, that behaves like 2, does it? Okay.
Yeah, so we can show that 1, like the surreal number 1 plus the surreal number 1 is the surreal number 2.
Okay, I'm worried that the definition for addition might be really complicated. So, but can I guess, is empty set on the left, 2 on the right, does that give me 3?
Yes, it would.
Okay, right, that works like 3, does it? Okay, I'm starting to get an idea of how addition. Oh, I don't know. Maybe I'm not.
So you can always verify this by using a definition of addition. So we can't have a set of all surreal numbers, right? As it would lead to. Okay, there are so many comments.
Yeah, chat goes quite fast sometimes.
Yeah, I'll try to go as far as.
I'll pick stuff out for you.
Yeah.
The question on the board said, how can we build them and what should we call them? I guess we're going to call them surreal numbers, but also we're going to call them. They have behaviour a little bit like 0, 1, and minus 1. We've kind of been giving them pet names along the way, like the 2 empty set one behaves a bit like 0, so people kind of refer to it as the 0 of the surreal numbers. That's a really weird concept. I think because the numbers you see at school, like even the complex numbers, the 0 of the complex numbers, it's just 0. It's just the same number, the same 0 as the 0 of real numbers. Whereas in a different system, like the 0 of vectors might be something like the 0 vector. It might look a little bit different. Here the 0 of surreal numbers is just a pair of empty sets. A bit like the 0 of water bottles is the empty water bottle.
Yeah. Okay, so this is like a system that you could build yourself. You could build a lot more complicated stuff by putting stuff on the left and right and experiment with that. But now I'm just going to give you like a general rule of what you would call a number, which is this massive thing here. So the question is written above. If we have x as a vertical bracket b, what should we assign this number to? So the graph below is like a generation of surreal numbers. So in the first generation, we can only have empty sets. That is the first generation. And in the second generation, we have minus 1 and 1 because we built that out of 0. And then in the third generation, we have plus or minus 2, plus or minus 1/2, because that's what we built out of 0 plus or minus 1. So this is like a generation of surreal numbers. And the claim here is that if I look at this number, the value of this number in the real world would be the midpoint between here and here. So 1 is chosen as the largest number that is to the left of this thing, and 2 is chosen to be the smallest number to the right of this thing.
Okay. So you've got some binary choices you're making, and you can locate those halfway the midpoints of your previous thing, like the lines on a ruler. You put them in, mark in the little dots. What do the black lines mean in your picture? How the kind of the way the generation is related to the previous generation?
Yeah.
How does that work?
So, like, do you mean these lines?
Yeah, like those ones. Like 1/2 is linked to 1 in the previous generation, but it's not linked to -1 in the previous generation.
Right? Yeah. So
that?
1/2 was 0 and 1. So that's how we build 1/2.
Oh, okay. So it's only built from that side of the family tree, sort of thing.
Yep.
Okay. Oh.
I guess the lines are just how people write it. If we would like link everything, that would be really confusing.
Ah, okay. But hang on, does this mean that something I hadn't realised yet is -1 on the left, the set containing -1 on the left, and the set containing 1 on the right? Is that not a surreal number? Is that not valid?
Well, so if we have -1 on the left and 1 on the right.
Oh yeah, I've got to think about the sets of this. Right, to do that comparison, I've got to think about the left and right sets of the surreal number known as -1 and the surreal number known as 1.
I guess it could be left as an exercise to show what number it is. One choice would be 0 because
Okay, so maybe it is a surreal number.
Yeah, so I guess the first thing to show that it is indeed valid, which I think it is. And then the other thing was to try to figure out the value that it's supposed to take.
How have we made so much out of essentially empty sets of empty sets? Empty sets are amazing. There's this older joke, older than this, that the set containing the empty set is kind of different from the empty set. So you could refer to that as like the one, and then the set containing this empty set, that's different again. It's not empty, and it doesn't contain the empty set. It contains something else. So that's like 2 levels of brackets, and you can build a model of the positive numbers out of this by just having more and more brackets. So that's kind of a joke about building the normal numbers out of brackets.
Yeah. So just as a reminder, actually this like the -1 case is actually like one case of this general rule of the first thing in between. So the first thing in between these 2 things are actually 0. The first thing that has been generated in between them.
Oh, so sorry, that's 1 on the right hand side, isn't it?
Yeah.
1 on the right hand side, and
yeah.
Oh, is this equal to 0?
It could be shown, and that's like an exercise because it's really not like something easy, because like this thing are complicated by itself. Even though it says 1 and -1, it's actually very complicated things themselves. So the claim here is that if we have something on the left and something on the right, so let's say this is the largest thing on the left and this is the largest thing on the right, then the value of this thing would be the midpoint between the largest things. So sorry, this is the largest thing on the left and this is the smallest thing on the right.
Ah, okay. So some complicated network of lines maybe for combining these things together. I
So
think.
if you have -2 as the largest thing on the left, and -1 as the smallest thing on the right, then the value of this thing would be -1 3/2. And I don't care what other things are there on the right. For example, I could have, so if we have, oops, -2, -1, we could have more things on the left, on the right. We could have like this entire thing, but we don't care all of these things. We only care about the smallest thing on the right.
So the behaviour, if you go and define addition and multiplication on this, it behaves a bit like just the leftmost thing in that.
Yeah, so these are actually the same number.
Oh.
But for simplicity, we just write it in this way because we only care about the largest thing on the left and the smallest thing on the right, and we try to find a midpoint between them.
That's a bit disappointing, I suppose, that the set we built it to have a set on the left and a set on the right, but I suppose it was comparing the elements. The definition was in terms of comparing elements, and then only the most extreme elements matter. That kind of makes sense. Only the most extreme elements matter, so you can define. You put your set down. This means that the thing somebody suggested in chat quite a while ago of 0, 1, 2 on the left, 3, 4, 5 on the right.
Yep. So
if you interpret those numbers as that they typed in chat, if you interpret those as surreal numbers defined by the thing we said about 10 minutes ago, then it's allowed.
But we could have like all of the integers on the left and empty set on the sorry, I'm trying to wrap up my mind. It's really confusing. But we can also build like if we have all of the integers that say 1, 2, and everything, this is actually valid as a definition. But it's not easy to think about any number that is greater. So if we want to find the largest number on the left, we can't, right? Because it's everything.
Oh no. Okay. So it's not just a case of taking the most extreme element, because they might be infinite sets.
So this is actually the infinity. Yes, it is. Infinity is a number in the surreal number system.
Oh no.
Yeah.
Amazing. Okay, so if you're allowed infinite sets around, which why not, then you can just write down a thing that behaves like infinity. And it's not even that weird. It's got empty set on the right hand side. Oh no.
I don't know if it's just me, but like I couldn't quite hear you clearly.
Oh no, sorry. How about now? Is this better?
No.
How about now? Is this better?
Yeah, it's
okay,
better.
Cool. My computer sometimes gets confused because I've got about 5 microphones plugged in from an experiment. The empty set, is the empty set bigger than infinity? Everything in the empty set is bigger than every number. That's the comparison we should be doing, right? I think.
Right. We're thinking about the things in a set, not the set itself.
Okay. Chat is impressed, I think, with that's infinity. Yeah, thanks for the reminder that I'm audible on stream. That is actually quite reassuring. I think somebody in chat tried to prove that 0 is equal to this kind of homework problem that you set by proving. Is it okay to prove if the left hand side is bigger than and if it's greater than or equal to the right hand side and the left hand side is less than or equal to the right hand side, is it okay to say they're equal as a result?
Yeah, we can define equal as that.
I guess I was right, says someone in chat, with the 012 idea, but I have no idea how we got to it or what my answer means anymore. Hey, person in chat, we redefined all of the things in your chat message to be really complicated nested sets containing nested sets, containing emptiness, containing the empty set, built in a complicated network of ways. And in that crazy world, everything's kind of consistent because we've just been stacking together all of these things to build new things. Manna, I don't think we've got time to play the game, but I think we can wrap up a little bit by... Is there maybe time to explain what the game is? Or should we put it in a further reading maybe? We can explain
Right, so the game is that If you look for surreal numbers online, you can actually see a lot of these games. So it is called hack and bush. So you have all of these sticks. You can do them in different ways. You can also have like these branches. You can even have circles.
Ooh.
Yep. So blue and red will represent the sticks of two players. So for example, if I'm red and James is blue, I can chop some of the sticks. Because I'm red, I can only chop the red sticks, and because James is blue, he can only chop the blue sticks. So for example, if I chop this red stick here, everything that is not connected to the ground anymore will just disappear.
Okay. And what's so we take it in turns and we do some chopping. We chops everything above.
So we're taking turns. So let's say if I cut this thing here, everything is still connected to the ground, and that's fine. And let's say if James cut this thing here, these things are not connected to the ground anymore, and they disappear.
Okay.
And then I can cut some red thing. I'll just do this one. And then James can only cut the blue thing, and I can cut the red thing. So the person who made the last cut wins the game.
Ooh. Okay, and I see. So it's complicated. You have some sort of complicated starting position, and then either it's a red player win or a blue player win, maybe, depending on. Okay, that's really cool, and it feels like cutting down trees, right? In the real world, not in Minecraft, where when you cut the bottom of the tree down, the top goes away as well.
Yeah. So I guess the situations could be, so if I can make a choice, will I choose to play the blue one or will I choose to play the red one? Does it matter if I go first or go second? So these are the possible strategies to play the game, and actually surreal numbers tell you which choice you should make. So the idea is that suppose we have this really simple situation where we only have this red one. I'm going to write on the left bracket all the positions that I can reach myself. So I can cut this one, and it would give me the nothing situation, which is the empty set.
Yeah, and I've got no choices that I can make. But yeah, fine, okay. From a red point of view.
Wait. So that's actually supposed to be a 0, not the empty set. Sorry.
Okay.
I could go to 0, and James has no choice, so he can only do the empty
right,
set.
okay, that's the difference. You have a move that leaves us with nothingness. I have no options because I have no blue sticks remaining.
So this turns out to be a number.
Well, it looks like a surreal number to me.
Yeah.
Oh gosh, I can't remember which one that is.
It doesn't matter.
Is it -1 or 1?
It's left to the audience to explore. Okay.
Okay.
And then we have this. So if we have this blue stick only, there's also like a value, right? So as the red one, I have nothing. As the blue one, you have 0. Okay, so now in our third game, we have this situation. So as the red one, I could chop this, and it gives me this situation, which is this game. So this is some value we're going to put down here. And as the blue one, you can chop this one, and it gives me this situation. So this is the value that goes in here.
So this is kind of the sort of set on the left. So someone said, is it used for analysing games? And I guess this feels a bit like you'd analyse almost anything with it, right? It's the set of all possible game states after your turn, any chess move or whatever, any bush chopping.
Right. So on the left, we have all the situations that I can get by chopping a red stick. And on the right, it contains all the situations that James can get to by chopping a blue stick. And this would be a number.
And then so you've converted the game state into a surreal number, and then is there a punchline? Like you just do something to the surreal number, like check if it's positive or negative or something? Or?
Right, that is actually very true. So I'm claiming that whether it is negative or positive implies whether blue or red is going to win the game.
Oh, that's mad. Okay. So if
And
you
you can
do,
check it yourself by playing some very simple games. And I'm also claiming that if this value is 0, it is a fair game in terms of blue and red, but it is the order of playing that matters. So whether I'm the first player or the second player will determine whether I can win a game or not.
that's brilliant. Okay, so whether or not we believe that kind of surreal numbers combining empty sets together, here's a kind of actual game where the positions in the game line up to surreal numbers. Your choices really rely on that nesting structure of surreal numberness, and apparently the way you convert them into a strategy is to do the same stuff that we were doing to evaluate
Yep.
surreal numbers. Brilliant stuff. Okay, there's some really long chat messages in chat, but I think we are now running over time, so I think we're going to wrap up in a second, if that's okay with everyone. Anything you want to say at the end of the stream, Manna?
Not really. I guess like there's a really good book on surreal numbers. It's kind of like structured in a way that we're structuring it. Because when you Google surreal numbers in Wikipedia, they just give you this really confusing graph, and it's hard to understand where things come from. But that book kind of tells you how to define things from the empty set, and I thought that was really good. I guess we can provide the book later on.
We can put a link in the further reading. So further reading
Yeah.
gets posted on the Maths Club website, link on the bottom of the screen and in the notes. Almost every episode comes with some further reading notes that we write after the show to point people towards other books and other bits and pieces. Thank you so much for being on the stream, Manna. Thank you for defining surreal numbers in all of their incredible weirdness. It's one of the best names, I think, for a maths thing. Thank you to Jade for moderating chat, and the researcher this week was Manna, the presenter was Manna, the chat moderator was Jade. So thank you to people watching. We'll see you again in 167 hours for another episode of the Oxford Online Maths Club. Take care. Good night.
Thank you.
We're getting more professional at the end, in that I've got to work out the phrase that I say. We're still live because I haven't worked out how to switch it off. Give me a second. Bye everyone. Super professional live stream.